when we develop new combinational circuits, the circuits themselves and the Boolean algebra expressions that represent them may be a little bit complicated to read. Not the individual operations, but we might lose the greater abstract purpose of the circuit in the more complicated expression. Certainly, we've already seen situations where the Boolean algebra expression for a particular circuit doesn't lend itself to understanding immediately when it produces a 1 as output versus when it produces 0. So in this lecture, we are going to look at a new form of Boolean algebra expression, a type of shorthand that we can use to make those details very clear. As well, that particular shorthand will allow us a mechanism to automatically produce a circuit diagram that is similarly styled from circuit to circuit to circuit, so that it's much easier for us to look at those diagrams and interpret what they do when. So to start, I want to remind us of a function we saw before. We made up this particular function in the past, so we have a function z that has 3 input variables, a, b, and c, and it takes the NOR of a and c and ORs that with the inverse of b ANDed with c, exclusive ORed with a. So this is a relatively complicated looking Boolean algebra expression, and we derived a complete truth table for it, the truth table for which I've only bothered to copy the output column here. But there were a lot of steps. We had to do a or c and then invert that for the NOR. We looked at the inverse of b. We ANDed the inverse of b with c. We took that, exclusive ORed it with a, and then had to OR the two halves of this together. And anywhere along the way, we could have made a mistake. But if we just look at the truth table, so once we've calculated the truth table for any particular function that we might want, or we might derive or design a truth table for a circuit that we don't know how to express yet, you'll notice that only certain rows have 1s and only certain rows have 0s. And very often what we care about is when the circuit outputs a 1. And so what we're going to do here is use a new shorthand that basically just says which rows have 1s in them. So to do that, we're going to use something called the sum of products minterm form. We'll also look at sum of products form in a minute. So sum of products minterm form. And you've heard this word minterm before. A minterm is just a shorthand way to identify a particular row in a truth table. So here I'll label one column for minterms, and what we do is interpret the input variables, however many there are, in the order they're described in the function definition or in the order they appear in the truth table. We interpret that as an unsigned number. So this is the 3-bit version of 0, this is the 3-bit version of 1, and then 2, and so on. 4, 5, 6, and 7. So what we can say now is that z, which is a function of a, b, and c, is equal to the sum of minterms, and we provide some set notation here, and we just identify the minterm rows where there are 1s. So it's 0, 1, and 2. And then 4 is next. Not 5, 6, and 7. All right. So what we've done here is we've provided a couple pieces of information. First, we provide the function name and the input variables. And because of the order that we provide the input variables here, when we look at these numbers over here, like the number 4, we can imagine a 3-bit number for 4 being 1, 0, 0. So we know that A will be 1, B will be 0, and C will be 0. So function name, input variables. And the set of minterms that are here, these identify the rows that output 1. Now, this is, of course, for some weird function, so we'll do this quickly for a function that we're very familiar with, like exclusive OR. So in exclusive OR, we have 2 inputs, and 0, 0, 0, 1, 1, 0, 1, 1. And only when one and only one of the inputs is a 1 do we get a 1 in the output. We get a 0 here. So this is minterm row 0, 1, 2, and 3. So we could say that exclusive OR is a function of A and B and is equal to the sum of minterms 1 and 2, because only rows 1 and rows 2 output 1s. Now, if you recall when we introduced Boolean algebra, ORing is represented with the plus symbol because ORing in Boolean algebra is equivalent to Boolean addition. ANDing in Boolean algebra is just represented by the concatenation of the variable symbols one after another, and that looks like multiplication in our traditional algebra, but that's because ANDing is multiplication in Boolean algebra. So if we think about this just a little, what we see here is, with this sum of products minterm form, is the minterms identify individual rows in the table. But really, that's just a shorthand like the 4. The 4 is really just a shorthand for A being a 1, B being a 0, and C being a 0. So if we can represent that as a set of variables, A, B, and C, some of them inverted and some of them not, then we have a product that represents that particular minterm. And so there'll be a product for each of these minterms. But then we OR them together, because effectively what we're saying, like with exclusive OR, we're saying that when A is a 0 and B is a 1, we can get a 1 as output. Or when A is a 1 and B is a 0, we can get output. And if there were more 1s, we'd say, or when that situation happens, we'll get a 1. So we take those products and then we OR them together, which means lots of little plus symbols. And that's why this is the summation, at least in the way that the equation appears here, the expression appears. This is a summation over a bunch of minterms. So the minterms are products, the summation is sum, it's the sum of products. And we call it the minterm form because instead of actually writing the long expression that has all of these three variabled products, with plus symbols between all of them, we can shorthand it by just identifying the minterm numbers. But let's go ahead and expand this out to the full sum of products form where we don't use the minterm. So to do this, what we can do is recognize that we have our function z of a, b, and c. And now what we need to do is expand each one of these. So I need a 3-variable product for 0. I also need one for 1, 2, 4, 6, and 7. And what will the 3 variables be? Well, they'll be a, b, and c. So I'm going to end up with 1, 2, 3, 4, 5, 6 different products based on a, b, and c, each of which are ORed together. So I'll just write a, b, c 6 times. Or a, b, c. Or a, b, c. There's 3. Or a, b, c. Or a, b, c. Did I do 6 there? 1, 2, 3, 4, 5. Nope. One more. Or a, b, c. Okay. Now, the next thing we need to do is, since these are all just a, b, c, this is incorrect. We need to make each product represent its corresponding minterm row from the sum of products minterm form. So the way we do this is very simple. Let's take, for example, I'm going to switch colors here because my black pen is dying. Let's take an example outside of these numbers for now. What if we were to look at a 3-input ABC type function and we wanted to know about minterm 3, right? So if we cared about what minterm 3 looked like, well, minterm 3, we can find it up here, has a 0 for A, a 1 for B, and a 1 for C. And so we need effectively a piece of digital logic or a Boolean algebra expression that will return a 1 whenever those conditions occur. And that turns out to be really nice and simple. So I'll do it as a circuit first. I'm going to write A, B, C and bust these down as I normally do. And then I'm going to put an AND gate because this is a product. All right, and I'm going to switch colors once again just to make it an extra point clear in a minute. So I'm putting the leads on some wires that I'm going to connect with over here. Now I'm going to connect my wires to this. There's C, there's B, don't forget your connection dots, and there's A. And now if you look at this, remember AND requires all of its inputs to be a 1 in order for us to get a 1 out of the circuit. So if a 0 comes in here, a 1 comes in here, and a 1 comes in here, which is the bit pattern we are hoping for, well, the 1 is going to come down for C, and it's going to go straight through this wire. Even don't worry about why this is red just yet. It goes straight through this wire into the AND. So we get a 1 here. When a 1 comes down on B, it's going to go straight in, and it'll remain a 1. But because of this inversion bubble, if A were to have a 1 on it, and it came down, it would get inverted into a 0. And then you'd have a 0 as an input to an AND, and it would produce a 0 as output. But if we have a 0 on A, the 0 comes down, gets inverted, and then we have a 1. So really, the same kind of thing could happen with B or C too. If B would have had a 0, then we wouldn't have a 1 here, we'd have a 0. Or if C were a 0 instead of a 1, we'd have a 0 here. And under any combination of those, this AND will produce a 0 as output. In fact, the only way it can produce a 1 as output is in the situation we have right here, where the bit pattern on A, B, and C is 0, 1, and 1. So if you draw out your AND gate like this, you can imagine yourself sort of standing there, and if you tilted your head over to the left, like this, then you would notice the parts of these wires, including the inversion bubble that I've drawn here in red, actually look like the 3-bit pattern for the number we want. 0, 1, 1 is the number 3, and it's the bit pattern we're looking for. 0, 1, 1. So this is a shortcut that I like to use to figure out what the gates are going to be. But it's only going to work like this when you're tilting your head over to the left. Also, when you connect all your wires in this rainbow style, right, where it looks like a ribbon cable of parallel wires coming down and then turning over to the side rather than having them bent over. If I were to connect A at the highest point, then B, and then C, it would still be the bit pattern. It would just read the opposite direction. So this is the way I always like to do it, and I think it makes my diagrams clean. So if we've got this, then that means the product for something that wants to say in a sum of products form expression, the actual product of the variables A, B, and C is going to look like this circuit for minterm 3. And for minterm 3, that is the circuit, the inverse of A, ANDed with regular B, ANDed with regular C. And soon you do this enough and you'll quickly discover that this shortcut of tilting your head and seeing the number written in the wires, that's got an analog over here. Whenever we see this inversion bar, that's the same thing as a 0. And when we lack an inversion bar, that's going to be the same thing as meaning we want a 1. So if I see the inverse of A ANDed with B ANDed with C, then I know that that means what we're really looking for to make this product fire off a 1 is a 0 in A and a 1 in B and C. So now I'll apply that back up here with our function z using the data we've got here from the sum of products minterm form. So I want the first ABC product to represent 0. So 0 is all zeros. If an inversion bar means 0, then I need 3 inversion bars. That is different than an inversion bar going all the way across. Don't make that mistake. A 1 is 0, 0, 1. A 2 is 0, 1, 0. A 4 is 1, 0, 0. A 6 is 1, 1, 0. And 7 is 1, 1, 1. And so with that, very quickly, we have now a complete sum of products expression. So when we write it this way, we call that the sum of products form. And this is nice because it has a direct relationship to a circuit that we can draw because it's a complete Boolean algebra expression, whereas this one is a shorthand for one. But there is no difference between what this represents and what this represents. So very often we like to communicate using something like this, the shorter minterm form, because it's very clear what it means. Even this requires some interpretation of, okay, a 0 here, a 0 here, and a 1 here. Whereas the minterm row identification, we can just draw the truth table immediately out and know exactly what function this thing is performing, or at least we would know it precisely in terms of when it produces a 1 versus when it produces a 0. All right, so let's draw the circuit out for this then, now that we know how this works. So if I have, I'll rewrite the function in sum of products minterm form. Z is a function of A, B, and C, and is equal to the sum of minterms 0, 1, 2, 4, 6, and 7. Then what I know I have is a function in the end, a circuit that has our 3 input variables. They're going to all be bussed down. I know I'm going to have a product for each of these 6 incidences, so I'm going to write 6 AND gates here. 1, 2, 3, 4, 5, 6. I also know that this is the sum over a bunch of variable products, which means it's the ORing of all of them together. So I'm going to put a grotesquely large OR gate that has as its output our function z, and then run a bunch of wires from the input end of my OR gate to the output of these different ANDs. And I'll try to do this as cleanly as I can. But this shape is this type of thing where there's a layer of AND gates followed by an OR gate is something we're going to see a lot more of, partly because it's trivial to take a truth table or how a function works and then derive its minterm form and therefore derive a circuit right from it that looks like this. But this is useful for other things as well. So as I did on the previous sheet of paper, I'm going to put in ahead of time my initial connections where I have inverter bubbles and where I don't, so that I can just think through these numbers. I'm going to make this top AND gate the one for 0, so I'm just going to denote this in these gates, although that's not really part of a normal circuit diagram. This is just to help me remember what I'm doing when I'm looking at each one of these. So now I can go right through and label the front end, the input end of this, with a regular wire or an inversion bubble. So for 7, for example, 7 is the bit pattern 1, 1, 1. 6 is the bit pattern 1, 1, 0. 4 is the bit pattern 1, 0, 0. 2 is the bit pattern 0, 1, 0. 1 is the bit pattern 0, 0, 1. And 0 is 3 zeros. So I just write those numbers from left to right going up. And then I always make sure to connect these where the top one goes to the rightmost thing first, and then continue. And that's the basic way we can come up with these circuits. Let's complete this one after another. No fun. In fact, this is mindless, but that's good. That's excellent. Because the more mindless such a process is, the more likely when we're in a situation where we need a circuit, we're going to be able to just make it happen because it doesn't require any kind of complicated activity. So we've got a nice shorthand sum of products minterm form expression here that we can instantaneously produce a circuit for. So as long as we can have a known function and identify what rows of its output will produce a 1, we can write this. And from that, we can trivially generate this. And this is effectively equal to a truth table. It's also effectively equal to the sum of products expression that we saw here, except that this is longer and not as easy to read as almost the original function is. So these are going to be the types of things that we desire. Now, that doesn't mean this is as compact as it could be, because if we go back to the original truth table here, while we have a 1 here, 1 here, 1 here, 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 and here, that's 6 ones out of 8 rows. So we had to document all that stuff, which turned into this big expression, which turned into a circuit that has all of these gates. But we could just as easily make this more compact if we recognize that there are so few zeros that we'd be better off doing this same thing and describing it in terms of zeros. So if this is the function z in sum of products minterm 4, and we wanted to identify instead when zeros come out, well, if we took the original truth table and we just invert z like this, we'll end up with 0, 0, 0, 1, 0, 1, 0, 0. Now I've got a new function, inverse of z, that only produces 2 1s as output, and in sum of products minterm form, that's going to be a pretty compact expression. Let's see here, that's 3 and 5. So let's write it that way. So I could say that instead of this, I could say that the inverse of z is a function of a, b, and c, and is equal to the sum of minterms in the set, what was it, 3 and 5. And that would automatically translate into a circuit that looks like this, but because it only has 2 minterms, it will only have 2 AND gates and the 1 OR gate that they go into. The only difference will be that this function doesn't produce the same thing that this function does, because this puts 1s in exactly the opposite rows that this one does. So when converting this to a circuit, A, B, C, I'll need my 2 AND gates, whose output will feed into an OR gate. That's a pretty sloppy looking OR gate. And this would be the inverse of z, but if I just introduce an inversion bubble here, then the function that was the inverse of z suddenly becomes the inverse of z, which by the double negative law is the same thing as z. So this makes my circuit much smaller. Let me put 3 here and 5 here. And 5 is 1, 0, 1, and 3 is 0, 1, 1. So I've primed my inputs. Now I'll just connect them, and we'll have an even more efficient circuit that implements our bizarre original function. Right? So now we've got another smaller, more efficient, more compact thing that provides the same capability. But most importantly, what those methods do is they make the description of the information, the way we can communicate the details of the function, much more compact and much less prone to any kind of error.